bientôt? Ok, perfect.
Oui, on a commencé. Okay.
Juste une question, l'exposé est en anglais?
Yes,
Oui, s'il te
I will
plaît.
switch to English.
We switch to English, yeah.
So welcome everyone. Today we have the pleasure to listen to Nicolas Burq, who will speak about propagation of smallness and control for heat equation. And this is a joint work with Ivan Moyanov. And Nicolas Burq is a professor at Université Paris-Sud. Well, thank you, Nicolas.
Okay, so thank you very much for the invitation. It's a pleasure to be online with you. So all that I'm going to speak about today is a joint work with Ivan Moyanov from Université of Nice. And so it's actually a very classical question that I'm going to study. So it's I will first present the results. So the classical question is about the null controlability of the heat equation on a manifold with boundary. So you take M with boundary, but for example, the M. So it can be a domain in RD. It's not a problem, but it can be something more general. And you look at a Laplace operator, which is the divergence for a density kappa composed with the gradient for a metric G. So it's actually 1 over kappa sum on I and J of D over dxi, J of x, kappa of x, D over dxj. So it's a Laplace operator in somehow the reasonable, the general form of a Laplace operator. And you want to null control the heat equation. So the question you want to address is something like that. dtu plus Laplace, or minus. Okay, dtu minus Laplace u is f, and we take f localized in a domain. So this is in R plus times M. You take boundary conditions, so you take either Dirichlet or Neumann. And you take initial data, let's say U0 in L2 of the manifold. And the question you want is to know whether you can drive U0 to 0. So G, here they said G is a subset of 0t times M. So it's internal control. I won't be interested in the boundary control, but probably we can get some results too in this direction. Well, let's say, of course, there are a lot of results in these problems, but now it will be some different results. Okay, and question, U0 given, does there exist F so that U at time t larger than t is identically 0? Okay, maybe I should have made a few assumptions on kappa. So you assume that your density kappa is bounded from below, and you assume that the metric G is definite positive. And I'll make some other assumptions a little later. So it's really some very standard heat equation. Okay, so of course there has been a lot of work on these classical questions, and maybe the starting results were due to Lobo-Robiano and Forsikov-Imanovilov in the 90s. And the answer is yes. So answer is yes. when, alors, first set of answer, it's you take G is 0t times omega open in M. And this is due to Lebeau, Robiano, and Fursikov, Imanuvidov. And so 95, around 95, something like that. And then to implement the strategy, so this method relied on its Kalman estimates. And so it requires some smoothness. So basically, everything was C infinity, so kappa and G C infinity, but then you can relax, at least if you don't have any boundary, you can relax to Lipschitz. DM is empty. Okay, and now if you want to relax the regularity assumption, when you have some boundaries, you have to work more, but you can do things, let's say. Okay, so it's the first set of results. Okay, and then there are some other sets of results. So let's say this one, for example. So in G is a subset F times omega, and now you assume that F has positive Lebesgue measure. So F is included in 0t. So it's just a positive Lebesgue measure set in time. So this is in time. And omega open. And now this result was due to Fung and Wang in 2013. Okay, and now you have some other sets of results. We'd say, okay, just a second, I have to close my door. Okay, okay, so now a third set of results, which is you take G of Lebesgue measure positive in 0t times the manifold. So this is a series of results, in particular by Aprais, Escoriaza, Wang, and Zhang. And here, the proof relies a lot on the fact that your Laplace operator is the Euclidean Laplace operator. So the proof, I will speak about the proof of all these results because it's actually intimately connected to the proof of our result. And the proof relies a lot, so it's a proof on complex analysis. Ingredients. Right, so it's something. So you really need the structure of the Euclidean operator. Of course, you could take some anisotropic Euclidean, but it's constant coefficients. It's really something where you really use. And even at the time, it was not clear whether if you put some real analytic smoothness assumption, you could say something. Okay, so I can state our first result. So it's the following. So theorem. So it's with Ivan Moyano. Last year. So the answer is yes to if G kappa are Lipschitz and G has positive Lebesgue measure. So you don't need anything related to complex analysis. So the result is a real analysis result, the kind of result that personally I prefer. You don't have to rely on any means on the magics of complex analysis. And you can also, of course, you also need some smoothness on your domain. So you need M to be, so the natural assumption when you have the metric and the density to be Lipschitz is the fact that your manifold is W2 infinity. You have a map, a change of, the maps which change which are in the atlas have to have this smoothness. Okay, so this is the smoothness which makes all your assumptions invariant by diffeomorphisms. Okay, so I will go because actually, so I will speak about we can relax a lot, and this will be later. We can relax a lot this assumption. We can actually, with the new approach that we have, we can get some results even for some observation domains which have measure 0. Of course, you have to change the setting of what it means to be exactly controllable. Okay. Okay. So now, what I'm going to do in the rest of the talk is to explain you a little bit how we can prove a result like that. So the good news is that in fact it's not difficult. So the difficult part was obtained recently. So it's difficult part in the proof. Are some results on harmonic functions by Logunov and Malinnikova. This is the hard part of the work, right? So it's I will explain to you a little later. Okay, so now let's go to the second part of the talks, which is we call you what the key tool in the proof. So my proof will rely on Lebeau and Robiano's strategy in some sense. So if I go back, it's an important thing, which are, yes, I should have said this, is that here, it's all the results we have, so it's a weak part in our results. All the results we have are for a Laplace operator which is time independent. Presently, we are not able to prove any result, any new result with this method, but we hope to be able to do it in the future for metrics or for operator which would be time dependent. So if you go to these results here, Forsikov and Imanouvilov method is perfectly well adapted to time-dependent problems, while Lebeau and Robiano is very well fitted for time-independent. So what I'm going to use here, since my problem is time-independent, is Lebeau and Robiano's approach. Okay, so let's go back. So what is the key point in Lebeau and Robiano's approach? So the key point is a so-called spectral estimate. So what is the spectral estimate? So you have a Laplace operator. So and you take an eigenbasis of the Laplace operator. En is lambda n square En. So the eigenvalues are non-negative, and it's lambda n square. And you define P lambda U is just some, well, okay. So it's 1 square root of minus Laplace smaller than lambda U. And so it's sum on the eigenvalues smaller than lambda of UN En. where U is the whole sum. Okay, so when you apply the spectral projector, you keep only the frequencies lambda, which lambda n, which are smaller than big lambda. Right? And now, theorem. There exists C for any lambda, norm for any U, say in L2, norm of pi lambda U, L2 of my manifold is smaller than C e to the C lambda, norm of pi lambda U, L2 of E, and now E. For any domain of non-negative, of positive measure, E, if the measure of E is positive, you can find C, and actually C depends only on the size of E, on the measure of E, Lebesgue measure of E. Right, so it's really something just in X. There's no more time anymore. It's just a result in X. Okay, so this result, well, this result was proved precisely by Lebeau and Robiano. So it's in this form, it's proved by Lebeau and Jerison. So the theorem is true. Theorem, okay, if. So first, omega is open, or E open. Non-trivial, of course. This is Lebeau, Jerison, Lebeau, Robiano. And this is Kalman inequality. So it's a consequence Kalman inequalities. So you can take G kappa to be, let's say, smooth, but basically Lipschitz is known to be basically the threshold at which you can prove Kalman inequalities. Okay, and now people started working on this. So there are some series of results which tells you that it's also true for Laplace is the Euclidean Laplace operator if E has positive measure, right? And so this is a series of results. So it dates back, it's actually dates back to Zygmunt in the 30s. And then you have Nazarov, Veselich, and many others, right? And so, as usual, so you see what I said, this is real analysis. This is complex analysis. So it's really something, it's completely different method of proof. So it was really something that people did not understand for a lot of time. Okay, so now theorem. So it's the theorem is also true for kappa G Lipschitz. And of course, when I say it's a plus boundary, it costs nothing. It's basically it's really that there's a little trick which allows to requires a little work, but it says that the presence of a boundary costs nothing. So it's Dirichlet or Neumann. Okay, so basically this is the key point to prove exact null control for heat. Okay, and this is real analysis. Okay, so actually it makes complete sense. You see, if you are able to do real analysis, it's better because it's more robust. You can really relax your assumptions compared to this. Okay, so but for a long time, so you see, to fix the ideas, this is the end of the 90s, 90, 95, 99. Okay, so and this is, you see, the complex analysis may improve approach. So this is in the 60s, 70s, right? And now this is really 2020, so 19. So it took a long time to really be able to get rid of the complex analysis method and to get the real analysis proof. Okay. Okay, so actually, we can do a little better. So you see here, question. What happens if we take some sets of measure 0? Well, of course, if you take a set of measure 0, the L2 norm on the right-hand side here is going to be 0. So it makes no sense. But you can switch from L2 to L infinity norm. And of course, you can show that this is, of course, this is it cannot have a too large nodal set, this function pi lambda of u, in some sense. And so you can expect that the L infinity norm will not vanish even for some sets of measure 0. Okay, so you hope to be able to go a little further. Okay, so it's actually indeed possible. So let's write this here. So theorem, second theorem, you have pi lambda u. Let's say you can put L2, but you can put also L infinity of m is smaller than c e to the c lambda. Okay. And now, what is the condition you want to ask? You want to allow E to have measure 0, but you want E to be not too small, because if E is really too small, then you can make sure that pi lambda of u is going to vanish at every point in E. So you cannot hope for any estimate. So what you have to do is something like that. It's the Hausdorf measure d minus delta of E has to be positive. Or for the people who know, it's basically, you can change this. You can have some quantitative estimates for if you put the Hausdorf content. And so what is delta? So there exists delta positive such that if this assumption is satisfied, there exists C such that for any u lambda. Right? So it's one step further. You can allow some sets to have, of course, for example, delta cannot be too small, but so you can allow some sets E to have measure 0, but Hausdorf d minus delta E is positive. So it's really, so what I mean by a positive Hausdorf measure is it's really that the Hausdorf measure, the d minus, well, it's exactly this. Okay. Okay. So can go a little further. Okay, so now if I go back, as I explained you, this theorem was the key to proving this null controllability result for the heat equation. Okay, so now I go back and ask the question, so what is the consequence of this spectral estimate? So the consequence of this spectral estimate is that you can control the heat equation on some sets with a control which is supported on some sets which are very, very, very small. So let's take the result. Theorem, so it's also with Ivan Mariano. And I do two things at the same time. I'm going to take some sets which are small in the x variable, and I'm also going to take some sets which are small in the t variable. So I take a sequence Tn, which tends to t not too fast. So it's smaller, not too fast. So what that means that Tn plus 1 minus t has to be larger than c Tn minus t, with constant c, which is positive. So it means that they cannot grow to t, capital T, exponentially fast. Well, faster than exponentially fast. They can go exponentially fast, but not super exponentially fast. Okay, I take E. Closed. This is technical reason. And now what I say is that I can control the heat equation, dt plus Laplace u equal. So I control the heat equation and I put some kicks. And the kicks are located at time Tn and on my very small En. So it's sum on n of delta T equal Tn tensor mu n. So mu n are measures supported on E. So it's I put some energy in the system and I solve this equation. Okay, so what does it mean to put this? So actually the measures are on some, it's easy to see that a radon measure is an element of some very negative order Sobolev space. So mu n are in some very negative order Sobolev space, but it doesn't matter because I solved the heat equation. So as soon as I solve a little bit, then it's going to smooth out everything. So it's going to be L2. And putting a delta times Tn just means that at T, I evolve the equation without right-hand side up to when T tends to Tn by values smaller. At time Tn, I add exactly mu n. So I u of Tn plus 0 equal u at Tn minus 0 plus mu n. Right? So I just up to Tn, at time Tn, I add mu n and I continue. Right? And now what I say is that for any u0, I can choose mu n so that the solution is equal to 0 after t. So this for any u0 in L2, there exists mu n such that the solution u at time t larger than t is identically 0. So it's really something. I control my heat equation, putting some kicks, which are localized both in time and in space. So if you look at the support of the measure, so the control F, which is sum on n of delta times t equal Tn tensor mu n. So it's supported in the union on n of Tn times E. So in terms of the measure of this set, the dimension of G, in time, the dimension is 0, right? So it's just a countable number of instants. So it's 0 for the time plus d minus delta for x. So it's smaller than d, and usual results is dimension of G is usually the dimension of, let's say, 0t times a domain, or an open set, or a set of non-zero Lebesgue measure. So it's d plus 1. So here you have a difference which is delta plus 1. It's really get some results on some much smaller sets. Okay, so that's for the result, the set of results we can get with this approach for the heat equation on a compact manifold. So of course, when you are at this point of the talk, a natural question is what happens on RD? So you switch M compact manifold to RD. Okay. So let's look first. I'm not going to state a result for the control of the heat equation, but what I can state very easily is a result for the spectral projector. So in that case, you need to make an additional assumption. So you ask the same questions. You put pi lambda is 1 square root of minus lambda. Laplace operator is smaller than lambda, so it's a spectral projector. And you want to have an estimate like that. Pi lambda u L2 over d is smaller than c e to the c lambda I lambda u, let's say L2 of omega, right? So when is this kind of estimate true? Okay, so it's not difficult to see just by some translation arguments that omega needs to satisfy some estimates, some geometric properties. So it's the following. Okay, I'm going to state the geometric properties. So assumption is the following. You took at a lattice. So it's you put RD is the union on P in ZD of the cube centered on P. So QP is the product from J equal 1 to D of PJ plus 1. Right, so it's just to put a picture like that. You have your lattice. It's Q0, Q10, and etc. Okay, and now your assumption is the following. The most natural assumption is you assume that the measure of omega QP has to be larger than C positive for any P. Right, so you have to put some measure uniformly in each cubes. So for example, let's draw a picture of a possibility for omega. You take a domain, and now you divide it in two with the same measure. And now you divide it in more pieces, so that the sum of the measures is always the same, right? So it's really, so you put more and more and more pieces, but the measure remains bounded from below in each cube. This is this assumption. It's very, oh, sorry. There exists C for any P. So the constant C here is uniform with respect to P. Right? So it's exactly this picture. You distribute the measure in small, tiny pieces. So typical example of domain which satisfies my assumption. So this assumption was actually first appeared in some control-related results, in some results by Moyano and Le Rousseau. Okay, so now theorem, under assumption A, you have the spectral estimate is true. Oh, now, assumption, first, Laplace is the Euclidean. So it's also some results in holomorphic functions. It's complex analysis. And now, more recently, so it was really a result on Fourier transform. So it's uncertainty principle. So it's really something about the Fourier transform. It's not even complex analysis. And now, recently, in 1919, there's a result by Lebeau and Moyano, and you have to ask for metric G, and the assumptions were G was identity plus G tilde, and G is tilde is real analytic plus small at infinity. Right, so it was a perturbative result, and it's a nice proof which relies on Kalman estimates for the D-bar operator. It's really it's a mix. So now it's really a mix of complex analysis and real analysis. Okay, so what I claim is that you can relax this all the way to Lipschitz. So theorem, the same result is true for G kappa Lipschitz uniformly on RD. Assumption 8, of course, and same assumption. Okay, so it's just this. So you don't even have. You can also drop. You can drop the small perturbation assumption. For example, for periodic metrics, is going to work. Okay. Okay, so now it's well, it's perfect. So it's a good time to start with the last section of my talk, which will be to give you basically essentially the proof of the main results, or at least the great part of the proof of the main result, except that I am going to cheat, of course, because I will assume the results by Logunov and Malinnikova. So now is the time to speak about the main ingredient in the proof. So it's third part of my talk. So it's Logunov-Malinnikova propagation of smallness. Okay, so what they do is the following. It's a basically local result. I look at it's a result about harmonic functions. I look at a Laplace operator, which is a divergence G gradient. I assume that G is Lipschitz. And I look at a harmonic function, Laplace U equals 0 in a domain omega in Rn. And I look at another set, which is K, so that the closure of K is included in my open set omega. I take a domain E in omega, and I make the assumption that E is positive or has a Hausdorf dimension at least D minus delta. For some delta positive exists. Okay, then norm of U L2 of K is smaller than C, norm of U L2 of E, or L infinity of E, depending. Alpha, norm of U L2 of omega 1 minus alpha, or L infinity of omega. Right, so you choose, if measure of E is positive, you choose L2, 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 and if E is smaller, you have to take L infinity. Right, you don't have a choice, simply because if E has Lebesgue measure 0, then the L2 norm on E is going to be 0. And so it's big U everywhere. And so, plus, so actually, it's even better. You can, if you replace U by gradient U, you can relax enormously the assumption on E. You just need to assume D minus delta minus 1 of E to be positive. Or, okay, exactly this. So it's really something has nothing to do with heat equation. It's just a result on harmonic functions. Okay, and so now the rest of my talk will be to try to convince you that we can use this result by Logunov and Malinnikova as a black box to prove spectral estimates on the manifold. So I'm going to reduce the analysis to the case where the boundary is empty for the spectral projector. Okay? Okay, so now how do we switch from pi lambda u to a harmonic function, u? So it's actually very easy. You define u is, so in terms of spectral, it's hyperbolic sine of square root of minus Laplace t over square root of minus Laplace pi lambda of u. Okay, so if I decompose u in terms of coordinates, so u is sum on n of un en. So I started with my Laplace g en, which is 1 over kappa di gij d kappa dj en, and this is lambda n square en. And now I have no boundary conditions because I said I'm not going to complicate things with boundary conditions. Okay, so and now of course I recall that pi lambda u is sum on n, lambda n smaller than lambda of un en. And u is going to be, so u will depend on t and x. So this depends only, pi lambda u depends only on x, but big U depends on t and x. It's going to be sum of lambda n smaller than lambda of sh of lambda n t over square root, oh, it has no square root, sorry. Lambda n un en of x. Okay, so I start with pi lambda u, and I define my function big U. And of course, it's very easy to see that dt square big U, when I apply dt square, I will take two derivatives of the hyperbolic sign, which will give me lambda n square in front, and lambda n square is minus Laplace of en. So this is going to be plus Laplace g, so it's 1 over kappa of di jij kappa dj. U is now 0. And of course, I can multiply by kappa, kappa. Okay, and this is dt kappa. So kappa depends only on x dt. And so it's plus something, 0. So it's a Laplace and tx applied to u. So it's starting from pi lambda u, I can define a harmonic function by adding one dimension, a time variable. So this idea actually dates back to the strategy of Jerison and Lebeau. Okay, so now what I'm going to do is I'm going to apply Logunov and Malinikova's result here to my harmonic function. Or maybe I should have drawn a picture about this result. So I can draw the picture here. So have big omega you have k, which is little smaller, relatively compact, and you have e, which is much smaller, and with the gradient, it's even much smaller. So this is k, and I have e, which is something like that. Oh. Okay. Okay. And okay, so maybe I should also have explained why this is propagation of smallness. So it's a quantitative uniqueness result. This result tells you that if U vanishes on E, then it vanishes on K. And actually, since K is arbitrary in omega, it tells you that U vanishes on the whole of omega. A harmonic function which vanishes on a set not too small vanishes everywhere, right? But it's better because it's quantitative version. If U, big U, is small in E, then it has to be small in K, provided it is not too big in omega. You see? Small in E, here. Small in E, the set E, implies small in K, due to this estimate. Okay. Okay, so now how do we do that? Well, it's actually quite easy. We just apply Logunov result, and we get gradient U. Oh, sorry. I should have written here, I should not have written E. Let's not take E. let's take G. Okay. It's the same, just change notations. Okay. And so now I do exactly this. I take L2, let's say, okay, L2 of G is smaller than C norm of gradient U, L2 of G to the alpha, norm of U, L2 of omega, oh, this is to the 1 minus alpha. And on the left, it's not G, it's K. Okay? Okay, so what I do is the following. I take omega is minus T, or minus 1, 1, times M, my manifold. Let's say I work locally, but it's not a problem. So it's I could take for the L2 norm, I will take a smaller set of M, but I can take the whole norm under my M. I take K to be minus 1/2 times the ball, say 1. And I take G to be 0 times E. So 0 in T times E in X. Okay, so I can do this. I can do this because I have minus delta minus 1. So I take very small sets. So I take a set which lives only in the X variable and there's nothing in the T variable. Okay. And now once I've done that, well, I basically have my result simply because you see, you just remark that gradient is gradient Tx and dt u and time t equals 0 is I lambda u. It's just here. If I take, oh, here. If I take one time derivative, I will have lambda n hyperbolic cosine at time 0, this is going to be 1. And I have lambda n, which compensates for this lambda n, and I get the sum of un en, which is exactly pi lambda of u. Okay? And so I should have taken L infinity norms because it's a little better. Okay? And now what I say is just this norm of gradient u, L infinity of minus 1, 1 times the ball is larger than the norm of gradient dtu, L infinity of 0 times the ball. And so this is norm of pi lambda u, L infinity of my small ball. Okay, so the left-hand side controls norm of pi lambda u, L infinity of my ball. Oh, it's x0. Okay, now G is exactly here 0 times EX. So this is equal to the norm of pi lambda u, L infinity of E to the alpha. So this is exactly what we want to have on the right. And now the last thing we have is to bound this by the norm of M, the norm of U in M, of pi lambda U in M. Okay? So now the last bound is norm of u L infinity of -1, 1 times m. This is the norm, or it's easy to see that it is smaller than c e to the c lambda norm of pi lambda u L2. Well, where does it come from? Or maybe there are some powers of lambda too. Well, it's just okay. So where does it come from? It just comes from the fact that here in the hyperbolic signs, here you have exponential of lambda t. T is between 1 and 1, so this is smaller than e to the lambda. Okay? And so you get, essentially what you get is just that this e to the lambda will give you this exponential, because little lambda n is smaller than capital lambda. Okay? And then to switch from L infinity on the right to L2, it's just Sobolev injection. So it's, you have to add some, here you have to add some lambda to some power. Okay, so this is smaller actually than c e to the c prime lambda, norm of pi lambda u L2 of m. Okay? Okay, so once you've done that, what you proved is this. Norm of pi lambda u L infinity of a small ball is smaller than c e to the c lambda with different constants, norm of pi lambda u L infinity of e to the alpha times norm of pi lambda u L2 of m to the 1 minus alpha. And now it's just, you just work a little by something like that. A to the alpha, b to the 1 minus alpha will be smaller than c epsilon a plus epsilon b, right? And so what you're going to do is that, of course, this controls the norm L2 in same thing. And what you're going to do is that this, using this and adjusting the constant, you're going to be able to put this term on the left, because it's L2 norm, L2 norms. Of course, this is on the whole of M in the right, in the small ball on the left, but you can apply this estimate for a finite number of balls covering M. You sum all this on the left, and you do this, and you get your exponential estimate. So it's really, you just play a little bit, you work around, and you get estimates like that. So it's okay, so last thing is, I didn't speak about, so it's a path from M to a boundary, to the boundary case. So it's also a little work, but there's nothing really very difficult. So it's, what is difficult in the analysis is concentrated here on Logunov and Malinnikova, beautiful propagation of smallness result for harmonic functions. So this is really for harmonic functions. And once you've done that, this was the key point to prove that we can transfer the propagation of smallness for harmonic function to propagation of smallness for solution to the heat equation. Okay, so I think I am going to stop here, and thank you very much for your attention.
Well, thank you, Nicolas. Is there any question? So yeah, I'm sorry. As usual, I am the only one to upload. But
No, also me. Sorry.
It's the rule of the game.
yeah. Is there any question?
I have a question. I have a question to you, Sylvain. Est-ce que tu m'entends?
Yes, please go ahead.
Yes, yes.
Ok, Asia. I have a question. Peut-être que je vais la poser en français. Qu'est-ce que ça donne pour le contrôle ponctuel de la chaleur, votre résultat?
Alors, qu'est-ce que tu appelles le contrôle ponctuel?
C'est-à-dire que tu contrôles, tu contrôles en fait sur des points X, mais je suppose sur des temps. Donc sur un point X de 0 et sur des temps. Et ma question aussi, c'est est-ce que ta suite Tn, tu as pris des conditions qui sont valables quel que soit l'ensemble E, avec la condition sur la mesure, d'accord? Et est-ce que tu peux ajuster ta suite Tn à delta? C'est vraiment déconnecté, les hypothèses sur la suite.
Alors, dans notre...
Tu peux répondre en anglais.
Oh, okay, yes. So in our proof, it is completely disconnected. So you see the argument with the set E is really completely located in this part. So you pass from this result to proving the spectral projector estimate. Okay, this one. Yes, this one. Spectral. Oh, well, this one, for example. Yes, for example, this one. So you see, it's a spectral projector. Okay, so this is only an analysis in the X variable. You see, the time variable which appears at the end of my proof that I presented you has nothing to do with the time variable in the heat equation.
Yes, I know, I understand. Yeah,
okay. Okay, so and then to pass from continuous time to discrete times like that, it's just functional analysis. You have to be careful, but it's functional analysis. It's completely two disjoint proof. So nevertheless, it's a very good question to have, because so we have the apparition of this this assumption on the fact that the sequence of time cannot go to t too fast. And what I think is that it is optimal, but presently I'm not able to prove it.
Okay.
So you see, it's okay. Of course, in all this business, you can translate the result in some observation estimate. And what I think is that the observation estimate at discrete times, if you take times which converge, so in that case, they're going to converge very fast to 0 because you're going to a chance. And then the observation estimate is going to collapse. But I don't know if it is true or not. So I think that for me, the real expert for that is Luc Miller. That well, at least the real expert I know of is Luc Miller. But I'm not an expert on this for me.
Okay. So for the point,
for the point, you know that there are some obstructions if you took even in one dimension.
No, I am yes in two, but
yes,
in one dimension you can consider.
In one dimension, in one space dimension, there are some obstructions. If you take
yes, there are obstructions, but you can assume that the point satisfies the uniqueness.
Yes, you can assume that they are not in any. Okay, so you can also do something like that. You can assume that they are in the nodal lines of no eigenfunctions in higher dimensions.
Exactly.
And I don't know.
Okay.
I don't know.
Okay, nice. Thank you.
Yeah, Jean-Pierre.
Okay, I have first one comment. I think that in RD, your condition on omega intersect QP non-empty should be valid only outside of the big ball.
Yes, absolutely. Well, actually, you don't have to. You can change the cubes by any larger cubes.
Okay.
And if you take cubes large enough, if it's valid in the outside of a ball for fixed cubes, it's valid for always if you take big cubes.
Okay.
You're right, Jean-Pierre, absolutely.
But my question is whether in the other case, whether you can take t equal tn and mu n supported in en.
Oh, the same kind of result as this one.
As
On RD?
No.
No.
With the en, you take en.
Oh, en.
Sequence en.
Yes.
Sets
Same
of,
proof. Same proof.
measure.
Same proof. Absolutely. You're right. I could take here. Yes.
Okay.
It's just because I didn't say it, but you see, it's
okay.
yes. If I go to Logunov and Malinnikova result, it's the constant here and the exponent alpha here. So alpha is of course positive. The constant depends only on some bound. So it's not a bound on the dimension, but it's a bound on the, I don't want to introduce what it is, but on the Hausdorf content. So it's something which is explicit in terms of some bounds that you get, which is a quantitative way of measuring the Hausdorf dimension.
Okay.
So the answer is yes. You can take this. You can play like that. So this is why, in some sense, in some weaker sense here, you see when I stated the result for the heat equation. Yes, this one. I also apply, so G is going to be the union on T of T times GT, right? And what I know is that for many times, for a set of times of measure non-zero, the measure of GT in X will be bounded from below. And now I have estimates and I play the same game.
Okay.
So
okay.
Yes, the answer is yes.
Are there any other questions? Okay, I will ask one. So you were speaking a lot about this result of Logunov and Malinnikova. Can you give us some insights on the proof? Or?
Yes. So actually, it's difficult, but it's not that difficult. Meaning, well, of course, we started with this, and we realized with Moyano that we could deduce some nice control for heat equation result from their result. And of course, the next step is that you want to understand their proof, because otherwise it's a little frustrating. You have a proof which uses something as a black box, but the thing you use, you don't understand it. So what we did, we set up a small working group in Orsay to understand these results. And basically, we had, how many? I think it's 5 workshops, 5 2-hour workshops. So it's 10 hours, were enough to explain the proof of the result. So it's not completely trivial, but you can do it in finite time. So what is the idea? The idea is the following. It's the basic idea. You start with omega, and I take K, and I take little omega. Okay? And if I want to prove my estimate, the same thing, norm of U, L infinity on omega, smaller than C, norm of U, L infinity on little omega, or let's say not, this is K, alpha, norm of U, or it's big U, L infinity on big omega, 1 minus alpha. I can just do Kalman estimate by taking a phase function which grows, which increases along some lines which enter omega. I write Kalman estimate with a parameter lambda, and I take an optimization on lambda, and I get this. Okay? So this is the same result, except that instead of having omega, a set of positive measure, you have a set which is an open set. Okay, and so now the main idea in Logunov method is to apply this by cutting the domains in small cubes and performing some zooms. Okay, so now why can you perform some zoom? Because if you want to perform some zoom, what you're going to do is just you are going to change u of x, big U of x, to big U of epsilon x. You zoom. Okay? And now, of course, if Laplace u is 0, well, this is u epsilon of x. Well, you get Laplace epsilon u epsilon is 0. Okay? And of course, it's just a simple calculation to check that Laplace epsilon is a family of Laplace operators, which is getting better and better the more you zoom. Because the coefficients are going to be closer and closer to constant coefficient operators. Okay? And so an important ingredient in this will be, in some sense, to apply some Kalman estimate. So it's, but they don't do Kalman estimate. They do integration by parts. So it's hidden Kalman estimates, but Kalman estimates is integration by parts, and perform this zoom to cut off your function into pieces. And then there are a little bit of combinatorial arguments, but very little.
Okay.
You zoom, you zoom, you zoom, and then you end up understanding what happens in some very small sets. But it's very clever. I think I don't know how he was able to. They were able to arrive to this proof.
And so here the Hausdorf dimension is d minus delta, and delta of, I guess it has to be smaller than 1.
Yes, otherwise we know the result is false.
But do you expect to be able to go up to delta equal to 1? Or what is...
Yeah, okay, so you know that if delta is equal to 1 is false,
yeah,
and the delta which is provided by the proof is very small.
okay.
And it's not clear. It's not clear. And I guess, to be honest, I'm not the good person to ask. Now I think I understand Logunov's proof, but it's a different story to understand the proof and to be able to really improve a lot on the result. So he would be the good person. So I think his conjecture is that it's true as long as delta is strictly smaller than 1. But he cannot, well, he is, oh, okay, so I'm sorry, it's not fair, because I always say he, because he's the one who was more involved in the technical parts, and she's the one who had the intuition and the idea that this method would deblock these kind of problems. Because, so actually what I didn't speak about is the fact that their result is on a completely different thing. On harmonic analysis, it's also an important breakthrough to understand some important conjectures, completely unrelated to control theory.
Okay. Thank you, Nicolas. Are there any other questions? Well, so if not, thank you again.
Thank you.
Thank you very much. It was a very nice talk. Thank you, Nicolas.
Not too fast.
That's perfect.
Well, no, not too fast. I have to rewind some parts, but it's okay. Thank you.
You still have the slides. That's the good point
yes.
of Zoom talks.
Yes. Thank you very much.
Okay, see you all.